Good morning, my name is Kaushik, and today my topic in CAD is about virtualization of CPU, memory, and I/O devices. Modern OS and processors permit multiple processes to run simultaneously. All processors have at least two modes, user mode and a supervisor mode. Instructions running in supervisor mode are called privileged instructions. Other instructions are unprivileged instructions. VMware Workstation is a VMware VM, so software suite for x86 and x86-64 computers. Kernel-based virtual machine is a Linux kernel virtualization infrastructure. CPU virtualization. Unprivileged instructions of VMs run directly on the host machine. Critical instructions should be handled carefully. Three categories of critical instructions: privileged instructions, control sensitive instructions, and behavior sensitive instructions. Privileged instructions execute in a privileged mode and will be trapped if executed outside this mode. Control-sensitive instructions attempt to change the configuration of resources used. Behavior-sensitive instructions have different behaviors depending on the configuration of resources, including the load store operations over the virtual memory. RISC CPU architectures can be naturally virtualized. x86 CPU architectures are not primarily designed to support virtualization because 10 sensitive instructions are not privileged instructions. The CPU architecture is virtualizable if it supports the ability to run the VM's privileged and unprivileged instructions in the CPU user mode while the VMM runs in supervisor mode. When the privileged instructions, including control and behavior sensitive instructions of VM, are executed, they are trapped in the VMM. Hardware assisted CPU virtualization. Intel and AMD had an additional mode called privileged mode level to x86 processors. Therefore, operating systems can still run at ring 0 and the hypervisor can run at ring 1. All the privileged and sensitive instructions are trapped in the hypervisor automatically. This technique removes the difficulty of implementing binary translation of full virtualization. So this is the memory virtualization diagram. So this is based on Intel hardware assisted CPU virtualization. So we have two rings, ring 0 and ring 3, where the ring 3 contains the apps and ring 0 contains the WinXP. And we have VMX root mode, which contains VM entry, VM exit, VMCS configuration, VMM, which is so these comes under memory and IO virtualization. We have VM control structure connected to and fro to memory and IO virtualization. So coming to the memory virtualization. Virtual memory virtualization is similar to virtual memory supported by modern OS. Modern x86 CPUs include a memory management unit and a translation look-aside buffer to optimize virtual memory performance. Two-stage mapping process should be maintained by the guest OS and VMM, respectively, virtual memory to physical memory and physical memory to machine memory. So this is the two-level memory mapping procedure. So where we have VM1 and VM2, which have the processes, and the outside we have virtual VA memory, physical PA memory, and machine MA memory. So each page table of the guest OSS has a separate page table in the VMM corresponding to it. The VMM page table is called the shadow page table. MMU already handles virtual to physical translations as defined by the OS. VMware uses shadow page tables to perform virtual memory to machine memory address translation. Processors use TLB hardware to map the virtual memory directly to the machine memory to avoid the two levels of translation on every access. IO virtualization. IO virtualization involves managing the routing of IO requests between virtual devices and the shared physical hardware. Three ways to implement IO virtualization are: one is full device emulation, second one is para virtualization, and the third one is direct input out. Full device emulation is about all the functions of a device or bus infrastructure, such as device enumeration, identification, interrupts, and DMA, are replicated in software. So this is a diagram of virtualization layer where we have guest device driver, virtual device, which the virtualization layer and a real device. Para-virtualization. So para-virtualization it consists of a front-end driver and a back-end driver. The front-end driver is running on domain U, and the back-end driver is running in domain O. The front-end driver manages the I/O requests of the guest OSs, and back-end driver is responsible for managing the real input-output devices and multiplexing the input-output data of different VM. So this achieves better device performance than full device emulation. Direct I/O virtualization. So it lets the VM access devices directly. It can achieve close to native performance without high CPU costs. Self-virtualized I/O. All ta- in this, all tasks are associated with. So all tasks which are associated with virtualizing an I/O device are encapsulated in SVIO. So which means virtualized input output. So this provides virtual devices and associated access API to VM and management API to the VMM. So this defines one virtual interface for every kind of virtualized I/O device, such as virtual network interfaces, virtual box devices. Thank you.